So we've been talking a lot about intermolecular forces without saying exactly what they were. Now we're going to talk about them. So they are electrostatic forces of attraction. They are forces of attraction between opposite electrical charges. As mentioned earlier, the strength of those forces determines what state the substance is at a given temperature. So we're going to talk about 4 intermolecular forces. The weakest one that all substances have is called a dispersion force or a London force, sometimes called a London dispersion force or a van der Waals force or an induced dipole force. It's got lots of names. I'll try to stick to dispersion forces because that's what your book uses. Dispersion forces are caused by fluctuations in the electron distribution within the molecule or within the atom. All atoms and molecules have electrons. All molecules and atoms have these dispersion forces. So the electrons, we learned, are in these orbitals, right? Which is just a region of space in which there's a high probability of finding the electron. It doesn't really say which part of it there is. It's in, it's just in that region somewhere. It's like saying that my 6 kids are in the house. Well, they could be spread out evenly. They could be all in their rooms or sleeping in their beds. Or like that one time, they were all on half of the couch. They were looking at something, and it was like, whoa. 6 kids on half the couch just randomly. It lasted for like 30 seconds, and then they went off on their own ways again. Electrons can do that. They can just spontaneously end up all on one side of an atom. So let's look at a helium atom. Helium atom's pretty simple. It's only got 2 electrons. So if we were to take a picture of the helium atom at various times, the first picture we might see, well, here's one of the electrons, there's another one, and over here there's one, and here's another electron. And then this third one, we caught both of the electrons on one side of the atom. The next frame, they'd probably be in different places, and it would be more spread out again. So this doesn't happen a lot, but it does happen. Just random fluctuation. Because both of the electrons are on the one side of the atom, they have the negative charge, this side of the atom becomes partially negative. The other side of the atom becomes partially positive. So it's imbalanced. We call this an instantaneous dipole. It's temporary. It comes and it goes, like the kids on the couch. They were there and then they're gone. I've never seen that happen again. Well, that instantaneous dipole in one helium atom has an effect on the neighboring helium atom. So this side of the helium atom is positive, and these electrons are like, ooh, look, that's positive. We're attracted to that. Draws these 2 electrons over. And now we have this attraction, very weak attraction, between the 2 atoms. That is the intermolecular force called a dispersion force. The instantaneous dipole in this helium atom attracts the electrons in the next one, induces a dipole, a spontaneous dipole in the other one, and we have another attraction here. This one can influence the next one, etc., etc. Now, by the time this one has gotten lopsided, this guy's probably gone back to normal, and so this is gone. These attractions are very weak. They're very temporary. They come and they go. But like being pecked to death by a duck, if you have enough little things, they add up to be significant, right? Or think of a fly, right? I've got flies in my house right now. And you're trying to do something, and a fly comes and lands on the top of your head. And you shake your head. And it comes and it lands on your nose, and you're swatting the fly, and it lands on your arm. The first couple times, it's like no big deal. But after 10 minutes of that, you're ready to blow up the whole house to kill the fly, right? It's just this little thing over and over and over again. These dispersion forces are very weak, but they happen over and over again. So I have an analogy for this. So If you think of these electrons as being like people on a ferry boat, or like one of the blue and white cruises that they have in the San Francisco Bay. And so normally the people are going to be, spread sort of uniformly around the deck of the ship, looking at stuff going around. Well, when the boat gets near Alcatraz, everybody wants to see Alcatraz, right? So think of this as being Alcatraz. All of the electrons are attracted to that side. The people are attracted to that side of the boat. And that may cause the boat to list just a teeny tiny bit, right? It'll cause a little bit of a shift. You go past Alcatraz and people lose interest and they spread out again. So that's what these instantaneous dipoles are like. I already said that. So how big that force is depends on how easy it is to get those electrons lopsided, and how easy they can be polarized by a dipole in a neighboring atom. So if you have a larger electron cloud, it's easier to get that lopsided than if you have a very small electron cloud. So larger atoms have stronger dispersion forces than smaller atoms. For molecules, we can't use molar mass alone to look at magnitude of dispersion forces, but we can use it as a guide when we're comparing similar types of compounds. So here we have the noble gases, and we learned that the size of the atoms increases as we go down. The molar mass of these also increases as we go down. Molar mass is roughly correlated to size, but not exactly, right? Because as you go across, molar mass increases, but size decreases. So we can look at the boiling points of these noble gases. The boiling point is determined by the strength of the intermolecular force, right? We talked about playing Red Rover, and if the Red Rover line, the intermolecular forces are weak, it does not take much energy to get through, right? So it'll have a low boiling point. If the Red Rover line is very strong, it's the football players with really strong grips, you have to be moving very fast to get through the line. You need a lot of kinetic energy. So in order for that substance to boil, you have to have a high temperature, much more energy. So we can see that boiling point reflects the strength of the intermolecular force. So helium is the smallest, it has the lowest boiling point. As the mass, the size of these atoms increase, the boiling point increases as well. Any questions? So we can use mass to help us decide which has the higher boiling point if the two things are similar. These things are similar. They are hydrocarbons. They're just carbon and hydrogen. So which one of these would have a higher boiling point? Which one's larger? The C2H6 is larger. It has a larger molar mass and it has more atoms, right? So this is the larger one. The dispersion forces are going to be stronger, and so we can predict that that should have a higher boiling point. That sort of question can be on an exam. The second force we'll talk about is the dipole-dipole force. And this is present in polar molecules. So atoms can't have this, only polar molecules. Polar molecules have permanent dipoles. We talked about this. They're lopsided, right? They have a positive end and a negative end. So they always have an attraction for the oppositely charged end in the neighboring molecule. So we've got the positive end of one dipole being attracted to the negative end of the neighboring dipole. So all molecules have dispersion forces. Everything has dispersion forces. Polar molecules have dipole-dipole forces in addition to their dispersion forces. So we observe that polar molecules will have higher melting and boiling points than non-polar molecules that are similar in size. So here we have formaldehyde. This is its Lewis structure without the lone pairs on the oxygens. And if we look at this and use my rules for determining whether this is polar or not, we look at the central atom. There's no lone pairs, so that's number 1 is true. Statement 2, all the atoms connected to the central atom are the same. That one's not true because oxygen is different than hydrogen. So my rules say this is a polar molecule, and it is. So the oxygen is more electronegative. This end is partially negative. The hydrogen end is partially positive. So what happens in formaldehyde is that the positive end of one is attracted to the negative end of the other. Like ions are attracted to each other, but this attraction is not as strong because instead of a positive 1 charge and a negative 1 charge, you maybe have a positive 0.1 and negative 0.1 charge, right? It's just a little bit of charge. But this force of attraction between the molecules is the dipole-dipole force. Intermolecular is between the molecules, not within the molecules. So here are 2 compounds, formaldehyde and ethane. They are almost identical in molar mass. When we look at their structures, though, we see that this one's polar and this one's nonpolar. I told you to remember that carbon-hydrogen bonds are considered nonpolar. All of these bonds are nonpolar bonds. If you have no polar bonds, you can't have a polar molecule. So hydrocarbons, just carbon and hydrogen, are always nonpolar. This one's nonpolar, this one's polar. They both have dispersion forces. Their similar molar masses tells us that the dispersion forces are similar in size. But this one has dipole-dipole forces, and this one doesn't. So when we look at the boiling point, this one boils at -19, this one boils at -88. This is much lower because the forces of attraction between ethane molecules are much, much weaker than for formaldehyde. Polarity also affects miscibility. Now that's kind of a funny word you might not have heard before. So you could think of it as mixability. That's not a real word, but if it helps you remember. Do these 2 things mix? Are they miscible? Are they mixable? The ability of a liquid to mix with another liquid without separating into 2 phases. So in general, if you have 2 polar substances, 2 polar liquids, they will be miscible. They'll mix together. 2 nonpolar substances will mix together. But if you have polar and nonpolar, they will not mix. And so what we say to help us remember that is like dissolves like. Like dissolves like. So if the 2 substances are alike in their polarity, they will probably mix or dissolve in each other. We mentioned this, that oily hands, oily stains on clothes, you can't get that out with just water. You have to use soap. So here we have an example of pentane and water. Pentane doesn't mix with water. Pentane is C3H8. It's nonpolar. Water is polar. They don't mix. Here we have oil and vinegar in salad dressing. They don't mix because the oil is nonpolar, the vinegar is polar. Here we have an oil spill from a tanker. The oil doesn't mix with the water. This is both a good and a bad thing. The oil is less dense, and so it forms a layer on the surface of the ocean. And that causes all kinds of problems for birds and stuff. So we need to be able to determine whether a molecule is polar. This is part of why we talked about shapes and Lewis structures and all of that. So the Book's method determine if the molecule has polar bonds, and then determine whether they add together to form a net dipole moment. That's using vector addition. Most 3A students don't like the book's method. This is my method. It works most of the time. Molecules nonpolar if both of these are true. We've said this before. No lone pairs in the central atom, and the atoms bonded to the central atom are identical, or they have the same electronegativity. So, determine whether each of these has dipole-dipole forces. So this first one, that looks like Cl, doesn't it? It looks like chlorine. This stupid font. The capital I and the lowercase l are exactly the same shape. So to avoid confusion, I wrote the name here, carbon tetraiodide. Well, if we're trying to figure out if these have dipole-dipole forces, we need to determine if they are polar or nonpolar. So the carbon would be in the middle, and the iodines would be around the edge. Do those 4 bonds give carbon an octet? Yeah, they do. Excuse me. Carbon tends to form 4 bonds. If we count up all the electrons, we'd find that we need to put lone pairs around all the iodines, but that's not absolutely necessary for this problem. Looking at the central atom, are there any lone pairs? No. And even without adding the rest of the electrons, could there be any lone pairs on carbon? No, because it already has an octet and it can't have any more. So no lone pairs. Are all of these atoms the same? Yes. So both of the conditions are true. This is a nonpolar molecule. Does it have dipole-dipole forces? No. Only polar molecules have dipole-dipole forces. So no. CH3Cl. So carbon, and it's got 3 chlorines and a hydrogen. And again, all 4 of those have to be bonded to the carbon. That leaves no place for lone pairs on the carbon. Carbon never has lone pairs in Chem 3A. Never. Okay, so carbon in the middle. There's no lone pairs, so that's condition 1. Are all of these atoms the same, or do they all have the same electronegativity? No. Hydrogen and chlorine are very far away from each other in the periodic table. Yeah?
Isn't it supposed to be 3 hydrogens?
Thank you. Yes. So we did a different example by mistake. Thank you for catching that. Oh, wait. Let's leave that one. It's supposed to be 3 hydrogens and 1 chlorine. So, yes, I drew the wrong molecule. Same result, yes. We still have 3 of one and 1 of another to the carbon, and so this is a polar molecule. So does it have dipole-dipole forces? Yes. All polar molecules have dipole-dipole forces. HCl. So that's just 2 elements. A diatomic molecule. These are much easier to determine if they're polar or not. If the bond is polar, the molecule's polar. So you can look up the values of the electronegativities. But I will not ask you any questions where my shortcut doesn't work. Okay, so what I say about identifying polar bonds is, are these 2 different nonmetals? Yeah, they're 2 different nonmetals, right? Assume that it's polar. The one exception is carbon-hydrogen. Now that's not always true, but it's true most of the time. And I won't trick you with that on an exam. So since these are different, that must be a polar bond, polar molecule. Does it have dipole-dipole forces? Yes. Any questions? What if it was iodine? Does that have dipole-dipole forces? No. We've got this diatomic molecule. These atoms are identical. So the bond is nonpolar, the molecule is nonpolar. This does not have dipole-dipole forces. Next one is hydrogen bonding. Hydrogen bonding is like super dipole-dipole force. Dipole-dipole force on steroids or something. Hydrogen bond happens in a polar molecule where we've got hydrogen bonded directly to fluorine, oxygen, or nitrogen. It's an extra strong dipole-dipole force. So these are going to be polar molecules. The reason this is extra strong is we have a large electronegativity difference between hydrogen and those three. These are the three most electronegative elements. And fluorine, oxygen, and nitrogen are also quite small, which allows neighboring molecules to get closer to each other. And so both of those factors cause the dipole-dipole forces here to be extra strong. So how do you remember what's needed for hydrogen bonding? We need fluorine, oxygen, or nitrogen bonded directly to hydrogen. Have you seen the movie E.T.? What did E.T. say? He would point at the sky in this pitiful voice, "E.T., phone home. Phone home. E.T., phone home." F-O-N-H. Phone home. You need to have fluorine, oxygen, or nitrogen bonded to hydrogen. If you have that, that molecule has hydrogen bonding. Hydrogen bonds sound like hydrogen bonded to something else, right? But that's a covalent bond. Covalent bonds are within a molecule. Hydrogen bonds are between different molecules. They are not covalent bonds. They are just super dipole-dipole forces. They're much weaker than covalent bonds, only about 2 to 5% as strong as a typical covalent bond. So let's look at hydrogen fluoride. So hydrogen fluoride, we have fluorine bonded directly to hydrogen. So this bond is extra polar. It's on the high end of polar covalent bonds. We've got a fairly large partial positive and partial negative. Over here, another HF molecule. This side is partially positive, that's partially negative. The attraction between the two molecules, the negative of one and the positive of the other, this is the hydrogen bond. Okay, so that right there, that's the hydrogen bond. This is not a hydrogen bond. That's a covalent bond between hydrogen and fluorine, but that's not what we call the intermolecular force hydrogen bond. Okay, I know that's confusing. Methanol, we look at this one and we say ET phone home, fluorine, oxygen, or nitrogen bonded to hydrogen. Well, here's oxygen, and it's bonded directly to a hydrogen. So this molecule will have hydrogen bonding. The hydrogen of one that's bonded to this oxygen is going to be attracted to an oxygen on the neighboring molecule. This dotted red line is the hydrogen bond, attraction between two molecules. So we can look at how this affects melting and boiling points. Here's methanol and ethane. Their molar masses are very similar. When we look at their structures, this one is all carbons and hydrogens. It's not polar at all. It's nonpolar. Here we have oxygen. This oxygen is bonded to hydrogen. So that's what has to be there for there to be hydrogen bonding. So this has hydrogen bonding. So we look at the boiling point of this one with just its dispersion forces, minus 88. This one has similar dispersion forces, but hydrogen bonding as well. Its boiling point is positive 64. That's a huge difference in the boiling point because the hydrogen bond holds the methanol molecules together much more strongly. Any questions? Water does hydrogen bonding. So we have this oxygen-hydrogen bond. So we have hydrogen bonds between the hydrogen on one and the oxygen on the other. It's electrostatic attraction between neighboring molecules. Hydrogen bonding is really important in a lot of physiological processes. You're probably aware that DNA has a double helix structure. So there are two strands and they're held together. What holds them together, the little ladders in here, are hydrogen bonds between the base pairs in the DNA. So we've got thymine and adenine. Here we have nitrogen and nitrogen-hydrogen. Here we have oxygen, and here's nitrogen-hydrogen. So we have that nitrogen-hydrogen bond, and so we can get two hydrogen bonds forming between these two pairs, between these two bases. Cytosine and guanine can make 3 hydrogen bonds. And so this is how cytosine and guanine always go together, and thymine and adenine always go together because they match. And so that is an essential part of DNA replicating. That's biochemistry, very interesting, but not part of this class. Okay, so we should be able to look at a question like this, which has a higher boiling point, HF or HCl, and the dreaded question, why? So comparing boiling points or melting points, you want to look at what sorts of intermolecular forces do they have, what's the strongest one? So these both have dispersion forces. Everything has dispersion forces. Are these molecules polar? Yeah. They're diatomic, and they're 2 different elements. We've got HF, and we've got HCl. So they're both polar. They both have dipole-dipole forces. So far, they're neck and neck. Does either of these have hydrogen bonding? Yeah, HF does. Fluorine, oxygen, or nitrogen, phone, home, H, hydrogen. So this has hydrogen bonding, which is extra strong. So this has the strongest intermolecular forces, which means you have to get it to a much higher temperature before it can break loose. So HF has the higher boiling point. And why? It has hydrogen bonding. So it has hydrogen bonding, stronger intermolecular forces. Intermolecular is a really long, annoying word, so we often abbreviate it IM. The last force I feel is not technically an intermolecular force, but it is a force between particles. It's called the ion-dipole force. This can only occur in mixtures, and it happens in mixtures of ionic compounds and polar compounds. It's especially important in aqueous solutions. So when sodium chloride dissolves in water, the sodium ions and the chloride ions separate, and they go around in the water separately. They do this because there's a force of attraction between this negative ion and the positive end of the water molecule. This is the ion-dipole force. It's attraction between a dipole and an ion. The sodium also experiences the ion-dipole force, but here it's surrounded by the oxygen end, the negative end of the water. Any questions? So this is a summary, the different types of forces, their relative strengths, where they're found, and examples.